Let's talk about the molecules that are important for our cells and therefore important for our body. So for this, we have a long list of learning objectives. We'll cover this in 2 videos. So we'll talk about organic versus inorganic, what water does for the body, salts, acids, bases, pH scales, some key reactions involving water, and then we'll talk about our macromolecules, what they're made of, their structure, their function. We'll talk about enzymes, and then DNA and RNA, and we'll end with ATP. So inorganic molecules are small, and they usually don't contain carbon. So inorganic molecules, small, usually no carbon. We'll come back to carbon. The classic example of an inorganic molecule for the body is water. So 2/3 of our weight is water, and water is super important. Most of its key properties come from the fact that it's polar. So it has a high heat capacity, which means it's hard to heat it up. It's involved in a whole bunch of chemical reactions, and in the body, water also provides cushioning. Another classic inorganic molecule are salts. Again, cations and anions. A salt is any cation or anion besides hydrogen or hydroxide, OH-. So things like sodium chloride, those are salts. And they dissociate in solution. So what that means is normally they have that ionic bond holding them together, but when you put them in water, they're going to be surrounded by a sphere of water. So they're going to exist by themselves. And we call that salty water solution an electrolyte. Electrolytes are super important for our body because they conduct electrical currents. So we need them for our contracting muscles and our firing nerves in our brain. And solutions can either be acidic or basic. So bases are things that release hydroxide ions, they release OH-, and we call them proton acceptors. They're going to take those H pluses. In biology and chemistry, right, H plus is also known as just a proton. Acids release proton ions. They release H plus ions, and they're proton donors. So they're going to be put into solution and they're going to give off H plus. And we measure how strong of an acid or a base something is by the pH scale. So we have high numbers are very basic. Another way to say basic is alkaline. So very alkaline solutions are things like oven cleaner and ammonia and bleach and egg whites. And then acidic things are shown here with small numbers, things like lemon juice, wine, coffee, etc. All the good things in life are acidic. And this is a log-based scale. So what that means is if you're going from lemon juice at a pH of 2 to a wine at a pH of 3, you're changing one number on the pH scale, but because it's a log-based, you're actually changing 10 times. So wine to lemon juice, we're going 10 times more acidic. We're going from a pH of 3 to a pH of 2. It's not just 1 time more acidic, it's 10 times more acidic. Again, you can think of it as that number tells you how many zeros, right? So 1 is 1 0, which means 10 times. Organic molecules, on the other hand, so inorganic, right, are salts and our water. Organic are carbon-based molecules. And we talk about monomers, which are simple molecules, and polymers, which are chains of monomers put together. And to create polymers, we're going to do a dehydration reaction. So we're going to lose water when we join together 2 monomers. And the opposite is true for hydrolysis. So hydro meaning water, lysis meaning break down. We're going to break it down with water. Add water and you can take your polymer and make a bunch of monomers. So in this video, we covered a few things. We covered organic versus inorganic, we covered acids versus bases and the pH scale, and we end with dehydration and hydrolysis. In the next video, we'll talk about some of those macromolecules.